So just a quick background to the presentation about who I am. I'm working in one of the business units in ST in a methodology group, and we're advising and providing methodology on low power flow verification, implementation, sign-off throughout the flow. And we've been working on this in our division, in our business unit in ST for probably 4 or more years. But as I mentioned in the slide here, we've been using up until now CPF. So that's something I'm going to talk about a little bit later, about the change now, because we're moving to IEEE 1801 UPF. Purpose of this presentation, really two things. It's almost like two presentations in one. One is to share some tips and some traps that we found during the last few years of low power verification on SOC designs. And the second thing is to share some experience of moving from CPF, power intent, to UPF 1801 on the project that we're doing now. So first of all, here's the general stuff, which is about some pitfalls in multi-supply verification. So it all seems like it's really easy to verify. When it's on, it's on. When it's off, and when it's off, you isolate. But of course, like a lot of these things, the devil's in the detail. So one of the things that we found in CPF, and you can do this since IEEE UPF as well, we were able to specify efficiently isolation in terms of supplies. So we isolate between one supply and another supply. I've just written some pseudocode here because this applies to CPF and UPF. A common problem, and one we've just seen again, it seems to come up on almost every SoC, is where the value that isolation clamps to, the generic value, applies to most of the signals, but you'll get a few signals where it doesn't apply, and often these seem to get forgotten. So, for example, the one I've given here, maybe an obvious one, is an active low reset, which gets clamped low and then puts the whole power island into reset. It's perhaps less obvious when you start to deal with things like test signals, where the test control might be clamped to the wrong value because of some generic clamping strategy, and that then creates an unexpected result during verification. And you can only find this sort of problem through functional simulation. Another flavor of the same trap, and this is these are all real experiences that came from SOC designs in Grenoble, in India, here in Bristol. This one, we had antifuses where we model the antifuse values through a file. The default values in the file are 0, and when the antifuse is 0, then the functionality is disabled in the SOC. What should have really happened is, instead of isolating the outputs of the antifuses, they should have been latched so that we preserved the value that was there. It's the static value in the fuse. What actually happened was it got isolated, and you don't find this if you're using the default values that are in the file. So you could actually get as far as silicon and realize that when you go into isolation, you've switched off some functionality on your silicon that you didn't expect. So it's a kind of a coverage issue, but it's a trap that we fell into once. Here's another problem around isolation. IPs that are in one power domain that have inputs that are tied high coming from another power domain. So the power domain supplying the input, it goes off, it's switchable. So because we've got an isolation strategy, we end up with an isolation cell there. If we haven't thought about the strategy, we can end up clamping that 1 that's coming into a 0. So you end up with the wrong value and you don't get the behavior you expected. However, it's a bit more complicated than that, because certainly in our implementation tools, and I think in most, the constant will get localized to be in the same power domain as the IP that it's feeding. So actually this problem, this isolation, virtual isolation cell, this clamping actually goes away altogether. So we had a difference here between what happened in simulation and what would happen in implementation. The solution was to run static checks and find this through a specific check and then fix the power intent. But also long term, we asked the simulator vendor to add a switch that allowed them to match the implementation tools. Here's some stuff about initial blocks in Verilog. So we've got a lot of places in our code where we've got initial blocks in models. By definition, they play once at time 0. There's a very simple example there. That's fine until we corrupt we switch off the domains where these initial blocks live. So in this example, clock and not reset get corrupted to X. When we repower up the domain, the initial blocks don't get replayed because they play once at time 0. So we end up with these X's staying there until there's another assignment. So we had to do workarounds. We had to deposit values on these, in this case, clock and not reset, to mimic what the initial block would have done. Long-term solution was to ask the simulator vendor to replay the initial blocks as though it were time zero, but there's a warning here, because if you just blindly replay all initial blocks, you might find that's over-optimistic for verification. You may be giving too much back. Still on initial blocks, here's an example, a very reduced example from an actual PLL model. And you can see what's happened here. I don't want to point because there's no pointing remotely. What's happening here is that inside the initial block is a forever loop, which is generating the clock. The problem here with this initial block is that when you shut down, the forever loop's still running. In fact, it will never terminate. So when you power back up again, it's not possible to replay the initial block because it was still running at the time of shutdown. It never completed. So actually, really, the problem here is just badly written code for anything which is going to shut down for power. So that we had to get the model changed. Well, you hack it locally and then you get it changed. So some issues here around corruption, and particularly around integers. We had a lot of problems around integer corruption in behavioral models. We've not just got integers in behavioral code. It's in synthesizable and parameterizable code. There's a lot of integers around in our designs. But there's no X value for an integer. This was a particular problem we had with VHDL. We've got quite a lot of VHDL in our SoCs. We tried various strategies for corruption of integers. So we tried, in conjunction with our EDA vendors, we tried setting integers to random values when we corrupt them. We tried setting them to their leftmost value. And we also tried corrupting integers to 0. Well, they all had problems. I've just listed some of the problems here. We got a lot of fatals. We got arrays that get indexed with an integer value that's gone out of bounds. We get divide by zeros. We get integers where they're at one of the limits of the integer range, and then the code is subtracting some constant, and now you're out of range of the integer. It's an underflow error. And then we also had even a corner case where the integer was being used inside a weight statement, and so we ended up with a negative weight value. So there's all sorts of little traps there. The long-term solution here was to work with our EDA vendors to try and develop more intelligent corruption of integers, understanding what's consuming the integer and then the corruption strategy being written accordingly. So now we've got a more dynamic strategy for corruption. One particular case here that I just thought was worth highlighting, because we fell into this whole VHDL conv integer, which we were using to turn stud logic vectors into integers. When you feed the conv integer with an X, you get a 0 out if any of the values going in X are X. So if I just show this little picture here, we've got some behavioral code. It's all inside the same domain. Some behavioral code feeding conv integer, which is then feeding a divide function. So the domain goes off, the X's come out, conv integer gives a 0, and we get a divide by 0 fatal. And it took a little while to figure out what was going on here. The long-term solution, again, was more intelligent corruption control, spotting that there was a downstream consumption of this value by a divide. Sorry about the titles on the slides. I don't know if they translate across non-English speaking sites. This is just one last comment. Simulation forces, it might seem obvious this, but simulation forces, we use them to work around bad models and also to do debug. In our simulator, and I would guess probably in other simulators, I'm not absolutely sure, when you switch off and you get an X, that takes precedence over the force that you've applied. So we think that's probably the correct behavior. However, the trouble is that when you power up, the forces don't come back. So you can end up, and we did end up, spending time trying to debug problems where we had code which was working before the power shutdown, but after the repower up, it wasn't working, only to find that somewhere there were some forces that had been set up ages ago in a file, and they've now gone. So the simulator now, we ask for an enhancement, now it reports when the forces are overridden during a shutdown. We get a list comes out in the log. We could have asked for an enhancement to replay all the forces automatically, but again, that would have probably been too optimistic. We thought that would have been dangerous. So we do it by hand, but at least we have the list now. So that concludes that little section. The next bit was about coming to UPF from CPF background. I'm here for time. Yeah, you're right, okay. Okay. I won't go through this in detail, but I've listed some reasons why we decided to change, why we decided to move. John's already mentioned about the convergence between the UPF, the IEEE standard with UPF and the CPF standard. So CPF fed into 1801, particularly more so now in 2013. Something that's quite a key point here, I think the fourth point on this list, is about third-party IPs coming with complex UPF files. So to be able to do UPF verification using UPF coming into the SOC, we had no way to translate that into CPF, so we were starting to face problems. So this is one of the reasons that we decided to move to a complete UPF strategy for our SOCs. So now we've got our first product on the way. So just to mention here, this is not by any means a complete feedback on the process of moving CPF to UPF. We're at the point now where we've found some things, and I'm sure we're going to find more because we're starting a project now. So regarding UPF tools, this is kind of where it hits the real world. The LRM defines a large set of syntax, but what's and a rich feature set, but what's happened is that the EDA tool vendors, not surprisingly, have decided to only support in that LRM what they think customers presently want. So you get this chicken and egg where customers can't use something because it's not in the tools, but at the same time, the tools aren't going to provide it because the customer's not using it. So what we did pragmatically was the first thing to do was to do a cross-vendor survey, try and understand what parts of the LRM the different tool vendors were supporting, and construct our own subset of UPF 1801 that we felt could be understood by simulators. We looked at a couple, ones that we're likely to use. We looked at static sign-off tools, and we also looked at implementation. So by the time you've done all that, it constrained the list quite a bit. And the result was what we've called internally at the moment for this project, UPF 2.0 minus, which is minus the things which are not supported across our tool set. And that list has now been rolled out to designers so that they're aware that if they stick within this table of commands and arguments, then they're safe for the flow. So here's one of the things that we faced early on to do with state definition, power state table definition. Coming from CPF, we were used to defining power modes like this. So you can see we start off by defining some condition, and this is written in CPF syntax. We start off by defining some condition, and then based on those conditions, we define one of the modes, the operating modes for our design. And we thought that seemed to map pretty well to UPF, the 1801 add power state, which does something very similar. You can see there, based on the supply expression, which will have some voltages in it, we define a mode, and then based on that, a particular operating condition, if you like, and then based on those operating conditions, we define a state, which is one of the states in our state table. That seemed like a good idea, and it especially seemed like a good idea because it's supported by mainstream simulators when we spoke to different vendors. Unfortunately, implementation tools today don't understand that. They only understand the UPF 1.0 power state table. And I think that's universal. I'm not aware of any implementation tool that understands add power state yet. So what that meant was we were going to need to have UPF 1.0 add port state, because in 1.0 you define the conditions on the ports, the supply ports. We're going to need the port state and the PST state for the implementation tools in our flow, but for verification we were going to have 1801 add power state. Well, maybe John can correct this later if it's wrong, but as far as I'm aware, the LRM doesn't define a relationship between these two ways of defining power states. They're orthogonal to each other. So there's no way for us to verify that what we're saying to verification is actually the same as what we're going to do in implementation. So the decision we took was to just use add port state as the 1.0 style PST. But there is a little warning here, which is that if you want to use something like corrupt on activity sim state, then you can't do that with a 1.0 style PST, UPF 1.0. So this was one of the limitations. This is an example of the kind of UPF 2.0 minus we had. Some things were rolled back to 1.0 because it was the only way to do them, that the tools understood. Something that was a bit of a mind change for us was coming from CPF. Well, I'll mention that in a moment. We've just talked about using add port state, defining PSTs in terms of the port state. That means that we need supply ports. So what I was just saying there, coming from CPF, we were used to being a bit more abstract, where with our HDL and our RTL at the beginning of the design, we didn't need to define supply ports. We had power domains, we had domain states, we had controls, but with the implementation details of supply nets and supply ports, we were leaving till further on in our flow. And that sat pretty well with the verification of the SOC Arch teams, because they liked the idea of not having to get their hands dirty with implementation details and just concentrating on verifying and designing the function of the design. With our 2.0 minus, though, we do have to define supply nets because we've got supply ports and we're writing our PSTs in terms of the ports. So right from the start, we're going to now have to go back to what seems like a less flexible solution, which is defining the names of our supply nets for implementation right from the beginning. So it's some heavier work for the RTL teams. And there is a little gotcha here because we need some collaboration with our physical designers to make sure they're happy with the names that we're calling these nets. It's not going to cause a problem. I think John's explained this well in the previous presentation. The 1801 standard does allow you to have an abstract way of working. He's talking about the refinement flow. We're well aware of that flow. But this is really just a problem with the tools catching up at the moment. So just a couple of slides here about the subject of hard macros. We're talking here in the context of low power about multi-rail macros, which are where you have a cell, something that's been hardened, and it has more than one supply pin. So you can imagine you've got a primary supply connection on the macro, but you've got some other supply that's needed to the macro, and so that will not be the primary supply. Examples we've got in our SoCs include things like PLLs, DACs, signal IOs. Our IO cells, for example, have an external supply and then an internal core supply, digital supply. We've got PHYs, some of our memories that have retention inside and then have a peripheral supply that can be shut off. So the way we defined this in CPF was to use CPF macro models, where we wrote a model for the cell and we had an automated flow internally for getting those from the cell design. And then we would map power domains from the parent power onto these cells, and that's the strategy we're using in our CPF verification today. It's just to highlight really the difference here with UPF. With the UPF tools today are using Liberty views as the reference for cells. So you can see in this code that I've put here, we're actually connecting supply nets to pins, which don't exist inside the HDL. They exist only on the Liberty view. So it's been a bit of a mind shift for us. I just said here, don't forget about the ground pins. I just showed the VDD pins, but there are ground connections. I didn't show them. The Liberty, it seems like a good choice because it's got the power ground pins on it. The HDL view doesn't. I think I'm right in saying that that Liberty was not something that came from the 1801 committee, not from the IEEE. It was something which the vendors introduced, or one vendor in particular. But you might think, well, how can I use Liberty in my verification because it doesn't have anything in it which is functional? It's just a static view of a cell, which is generally thought of as being used in implementation and sign-off. Well, it's got related power pins inside about the relation between the supplies and the input and the output pins on the cell. And it also can have a power down function, which defines a logical expression so that you can say this pin behaves this way when these supplies are in this state. So it does have some functional information in it. And it tells the simulator how to behave when the power supplies change. But we also have behavioral models, which may or may not be power aware in terms of understanding the supply states and what happens to the cell during the power down and power up. So the conclusion really here is that for safely modeling hard macros in verification, we're loading the Liberty files, the Liberty view, which must have these PG pin and PG type attributes inside it to work. And we're also loading the HDL behavioral view. And those views together, and this now becomes a bit vendor specific as to exactly how those views are used, but those views together define the behavior of the cell. Mike, okay, thanks. Just a little comment there that the IEEE has added macro models coming from CPF, but there's no tool support for that today. So, summary slide here, we're at the end. Coming from CPF to UPF, our general view was that UPF 1801 much more closely matches what we were used to in CPF than the old Accelera standard did, what people call UPF 1.0. However, the tools have not fully caught up yet on 1801. And it was interesting, there was a question earlier from somebody in Cambridge about the tool support for 1801. Even though the 2009 standard has been out for a while, some of the tools are still not supporting certain constructs there, certain what seem like quite basic constructs in some cases. So, for example, use a UPF 1.0 style PST if you can, because it will make things much easier through your flow for implementation. And check your tool chain to see what's actually supported. For us, it was a change in methodology because we had to define supply nets, in detail right from the beginning. We would like to use supply sets, that's another story. Check that the implementation team are happy with what you choose to do if you're writing this at the RTL stage, because it will affect them. Hard macro modeling, we're relying on Liberty and the HDL behavioral views. So you need to check that your lib models of your cells in your libraries have the correct attributes on the PG pins. Check that they have the PG pins. And you also need to check with your EDA vendor about exactly how their simulator will handle the combination of Liberty view and behavioral model, because I can't go into the depth of it here, but there's a lot of different scenarios there about whether the behavioral model is power aware or not, what's inside the Liberty, etc., etc. There's a lot more we could go into, but there isn't any time today to do that, as Mike's flagging me. But there isn't time. There are other issues here around VCT, around the value conversion tables. There are issues here around definition of power domain interfaces, high con and low con support. There are a lot of other little traps in here. Maybe there'll be a chance to talk about another time.
Cambridge.
Yeah, so the question here in Bristol is, how often are we updating the UPF 2.0 minus table, and is there a roadmap for it? The answer to that is we don't know, because we've constructed it for the first time, and at the moment it's frozen, I would say, it's frozen for the duration of the next project, let's say the next projects, which would probably be something like till the end of the year, let's say. After that, we'll review it, and if vendors are supporting more than when we first looked at it, it will change, yes. It's not frozen forever, so it will evolve as vendors add commands to their tools. And we're really hoping there'll be quite a big step forward with general industry support for UPF 2.0 in the next year, because certainly we're pushing heavily for it, and I think some other people are too. Thank you to Paul.